So both the statements in the question 6 means statement first says the Oro1 strengthening mechanism deals with the bending of dislocations around impenetrable solid particles when they are dispersed in a matrix, and statement second says the formation of Oro1 loops makes the dislocation motion difficult. This results in large work hardening. And so this statement is also correct. So the both statement 1 and 2 are true. Then coming to the next question, a composite which is reinforced with fine particles will have dash compared to a composite which is reinforced by coarse particles with all other variables same. So as the particle size reduce, the grain size means grain size strengthening will be high, means the heterogeneous small particles will be strong and dispersed throughout the matrix, while for coarse particle the interparticle spacing will be high. So the distance between particles will increase, and so the small particles means if d of particles is very low, that will lead to higher strength, means that will lead to grain size strengthening, more interfacial bonding with the matrix interface if the size is low. So the first option, higher strength, is correct, means reinforced composite with finer particles will have higher strength compared to a composite which is reinforced by coarser particles. Next question is says that in grain size strengthening theory, the presence of particles will refine the grain size after solidification or recrystallization, and a small grain size has more barriers to slip. Yes, statement 1 is correct. And statement second says the particle will act as heterogeneous nucleation sites with a lower nucleation rate. No, this is wrong. With the heterogeneous nucleation sites, the nucleation will be always high, means that will provide high nucleation rate. So statement 2 is wrong. So statement 1 is true and statement second is false. So C option is correct. In the 9th question, it is asked that which of the following statement is correct about work hardening in a composite material. First question says the presence of reinforcement causes interruption to material flow occurring in the matrix, leading to the generation of dislocation. Second option says dislocation tangles, this is tangle, can form around the particle due to plastic incompatibility. Correct. Third option says as deformation continues, geometrically necessary dislocation will be generated at lower strain. No. To maintain the continuity, therefore work hardening increases through forest hardening. So the geometrically necessary dislocation generate at higher strain. Always, means at low strain dislocation tangles form, and at higher strains geometrically necessary dislocations will form. So third statement is wrong. First and second statement is true. So the correct option will be C. In the next question, it is asked statement 1, The difference in thermal expansion coefficient between the matrix and reinforcement generates misfit strain. Yes. Then second option is the dislocation density is low near the interface. No, this is wrong. Dislocation density is high at the matrix particle interface. So statement 2 is wrong. Statement 1 is correct. So the first option will be right. So this is so the week 10 like problem solving session is completed now. The students can ask questions in the discussion forum also. I will be very happy to answer. And I will give a extra 2 hour session also at after completing the all week sessions, all week problem sessions. So thank you all. So and here the sigma m dash is the flow stress of matrix. At a strain corresponding to fracture stress of fiber. So if the stress in the composite is very greater than the stress for matrix, the equation will be written as the sigma fu ff plus sigma m dash 1 minus ff should be greater than sigma mu, and from this equation the volume fraction of fiber can be calculated as the ff should be greater than sigma mu minus sigma m prime divided sigma fu minus sigma m prime. So for a condition where the elastic modulus and strength should be higher, means for a composite to have high strength and modulus, the minimum amount of fiber should be there in the should be mixed with the matrix, means critical amount. So this can be written as the critical fraction also, means critical fraction of the fiber. So Fc is written as the sigma mu minus sigma m prime divided sigma fu minus sigma m prime. So this is required for strengthening, critical fraction for strengthening. And if the sigma Cu should be greater than sigma m, u 1 minus ff. So in the previous condition we used that the sigma Cu should be if sigma Cu is very greater than sigma mu, and here is the sigma Cu is very greater than sigma mu 1 minus ff. So for this equation, if we write sigma fu ff plus sigma m prime 1 minus ff is written as the sigma mu 1 minus ff. So F minimum will be sigma mu minus sigma m prime divided by the sigma fu plus sigma mu minus sigma m prime. So this should be the minimum amount of fiber fraction. And if a curve is drawn for the composite strength sigma c, and here is the volume fraction of fiber, this is for 0 and this is 1. So this for a increasing amount of fiber fraction, sigma m prime and sigma f is graph curve can be follow this line, and for the sigma mu where ff for this equation means this follow two equations. First is the sigma cu sigma fu into volume fraction of fiber plus sigma prime sigma m dash 1 minus ff. This is fourth equation, and this is the sigma cu greater than equal to sigma mu 1 minus ff. And this is 2. So this line is for the equation 1, and this line is for equation 2. So the intersection point will give the F minimum means minimum amount of fiber content, and if a line is drawn with sigma mu, this will be F critical. So here are some limitation of the rule of mixture. First is it gives the upper bound of properties. Because how it gives the upper bound means it assumes the isostrain condition, which is not applicable always at every point in the composite, and presence of it means does not it does not assume the effect of defects, means presence of defects will affect the deformation behavior and changing the stress, strength and modulus values. So it is only considered for assume isostrain conditions, and no absence of for the pure material where there will be no defects, then only this will give the upper bound of properties. Next so how the strengthening comes in the composite of in the fiber reinforced composites. So the metal matrix composite also follow a strengthening mechanism which leads to the increase in properties compared to their initial phases individually, matrix and fiber. So the strengthening mechanism, it depends on interface between matrix and fiber, and interface and the interfacial bond. Between fiber and matrix. Because due to the interfacial bond and at the interface, load is transferred from matrix to fiber at the interface only, means through interface. So the interfacial bonding should be very good for the effective increase in the properties. So the how load transfer is explained, that explained by a theory, shear lag, called as the shear lag theory. What is shear lag theory? Let's see. So if this is the fiber on matrix interface in a composite, means the fibers are dispersed, and this is tensile stress is applied. So for a single fiber there will be two forces, means of length L. Means the tensile stress is acting along this also, and at the interface a shear stress also work at the interface, that can be written as the tau naught, and at the the tau naught will work from the both sides, means at the interface, means it works on the L/2 length only. So if the strain hardening effect of matrix is neglected, then the shear will never achieve the yield stress, means tau will never exceed the yield stress of matrix if strain hardening is neglected. So for the L/2 portion, the force equilibrium can be written as the sigma F pi d square by 4 tau naught pi d and L/2. So from this equilibrium, sigma F can be written as the 2 tau naught L/d. So here the L/d ratio is the most important term in the interfacial bonding. And the critical length LC can also be written as the sigma F d by 2 tau naught. If L is greater than LC, then there will be chances of matrix yielding. And the average stress acting on all fibers can be written as the sigma F 1 minus beta divided by L by LC, and here beta is the load transfer function. So for the equation 4 which we derived earlier, that sigma Cu written as the sigma FUF plus sigma M dash 1 minus fiber fraction of fiber volume fraction. So sigma Cu beta divided by L by LC plus sigma m prime 1 minus ff. This term is included because this is the average stress in the fiber of the fiber contributing by the fibers in matrix. So here the LC term is coming. So LC we know this is sigma f d by 2 tau naught. So L by LC will be L by d sigma f 2 tau naught. So here L by d term is coming, means here also the L by d term is coming. So this defines the function and the effect of the fiber length on fiber dimensions on the composite strength and modulus. Fiber dimensions, these are the fiber. So fiber dimensions also have an important role with the interfacial bonding and the strengthening of the composite. So if L is very low, the strength will also less, means L is very low, so low strength of the composite will achieve. That's why the discontinuous fiber generate lower strength. While continuous fiber are provide good strengthening. Next is the dislocation mechanism. Means dislocations are also present in the composite, in the matrix, and in the composite with matrix phase. So next is first is the shear lag theory. Next is the shear lag theory, in which the shear stress exists at the interface of fiber and matrix that will lead to the variation in strength of the composite with the according to the dimension of fiber. So next is the dislocation strengthening mechanism. So how dislocation interact with the fibers or particle reinforcement. So the particles and fibers in the composites are very strong, and they cannot be cut by the moving dislocation. So these are, if we consider the impenetrable particles, so if two particles are assumed and dislocation is moving along this direction, then after coming to this point, the dislocation will go to the particles So the strength coming from this effect means the dislocation line will be hindered because of the these particles. So the strength will be Gb given as the Gb by lambda, where G is the shear modulus, B is Berger vector of dislocation line, and lambda is the interparticle spacing. This is the mechanism behind the dislocation and reinforcement strengthening. Next is the grain size strengthening. So how grain size strengthening comes in the composite? As these particles and fibers provide heterogeneous nucleation sites. The nucleation rate will be high, leading to finer grain size. Finer grains, and means there will be grain refinement because of the particles present. So this can be written as so the increase in strength can be written as with the Hall-Page relation. So sigma is written as the sigma I plus k d power minus half. So during solid state processing also, recrystallization happens in the matrix phase, and during recrystallization there will be particle stimulated nucleation. Particles are already present with the matrix, so the particle will stimulate the nucleation rate. That will lead to grain refinement. So the strengthening because of the grain size reduction is written. So D is the grain size, is written as the DI FI FF power minus 1 by 3. So here DI is the particle size, and F is the volume fraction of particles. Next theory is the work hardening theory. Means work hardening happens during the plastic deformation. of the composite. So how work hardening works? So during plastic deformation, the yield strength of the matrix gradually increase, means gradual increase in yield strength of the matrix this lead to long range dislocation glide. I mean, because as we know, the work hardening increases the yield strength of the material. So the gradual increase in yield strength of matrix lead to long range dislocation glide. I mean dislocation gliding. So this is at the where the fiber is not present. But when in presence of reinforcement, the reinforcement cause interruption with the dislocation flow, with the dislocation motion and matrix flow, material flow. Means there will be interruption in the dislocation glide also, so that lead to generation of more dislocation. More dislocations, and the dislocation tangles also form at the matrix reinforcement interface. Due to plastic incompatibility, because the matrix and fiber do not deform with the same behavior. Means fibers are brittle and matrix is ductile. So due to plastic incompatibility between matrix and reinforcement, the dislocation tangles form around the reinforcement particles. So due to these interruption, geometrically necessary grain boundaries are formed. Geometrically necessary dislocations, means GNDs form at higher strain. Means dislocations are at dislocation tangle is at low strain and GNDs will form at high strain. So due to work hardening, dislocation tangles, geometrically necessary dislocations and interruption of dislocation, interruption of material flow lead to forest dislocation, means and the formation of forest dislocation increases strength significantly. So for that, Ashby model of misfit strain. Next is the thermal expansion coefficient difference mechanism. So next mechanism is explained by the difference in thermal expansion coefficient. Means thermal expansion mechanism due to repeated heating cooling the misfit strain develop in the composite. Because the thermal expansion coefficient of thermal expansion is different for matrix and reinforcement. That will lead to stresses, that will lead to misfit strain in the composite. So the misfit strain is explained. The mechanism of the misfit strain strengthening is given by the Ashby model. So in the Ashby model, a particle is considered along the x1 and x2 direction, and if a force is applied along this direction, along the first is the x1 direction, then because of the deformation this will change into ellipsoid. The shape of the particle will change to a sphere, ellipsoid, because of the deformation. So so this is after expansion, when heating is done, and after cooling this ellipsoid particle will want to attain its spherical shape after cooling. And this is the spherical shape. So now the axis is also changed for this ellipsoid. This is x1 prime and this is x2 dash. So for attaining the initial shape, force will act on this along all four direction. So in the reshaping or achieving its initial shape, the deformation generates near the particle interface. So dislocations are coming out from the near the particle interface. This is called the punching of dislocations. Means because of this compression, again punching of dislocations. Means, and these are the GNDs, or also geometrically necessary dislocations. So with the GNDs, forest hardening occur. So due to the thermal difference in thermal expansion coefficient of thermal expansion coefficient, means coefficient of thermal expansion, lead to adding dislocation. And that at will create so difference in coefficient of thermal expansion will create misfit at interface that lead to dislocation generation and high dislocation density, high rho. So this model, so now this punching of dislocation is given by the Arsenault-She. So after the aqueous particle with dimensions achieved, the dislocation create at the interface. So how the dislocations are seen at the particle interface? If we draw interface, then the further dislocation will be of this type. Means the dislocations are created at the all surfaces. So this is how the dislocations are punching out from a particle interface. So the vectors of this can be written as the T1, T2 and T3. So the change in its strength due to the punching effect is given as the sigma d alpha gb square root of rho. Rho is the dislocation density. And here rho is given as 12 delta T temperature difference into delta B volume fraction of reinforcement divided by B dP 1 minus particle volume fraction. So delta B beta is the thermal mismatch, and delta T is the temperature difference. So this is how we can conclude that the different mechanisms act in the metal matrix composites for increasing the strength and elastic modulus. So first is the shear lag theory, in which shear stress act along the matrix matrix fiber interface. In the next theory, the dislocation interaction with the particle is considered, means Orowan strengthening comes. Next is the work hardening theory, in which the material flow is interrupted because of the particles. Second is the work. Then next is the thermal expansion coefficient difference that lead to the formation of porous dislocation by punching of dislocation from the reinforcement matrix interface. So now, the week 10 overview of the week 10 lectures is completed. We will discuss the equations, means assignment questions. So if we go through the question 1, so first question is asked that the punching of dislocations from the particle matrix interface is explained by the coefficient of thermal expansion mismatch. Second question is asked that statement 1 says the experimentally measured value of the property of composites is always lower than the value obtained by the rule of mixture. And statement 2, in the rule of mixture there are some assumptions like isostrain and the presence of zero defects in composites. So both statement and statement 2 are individually correct, and statement 2 is the correct explanation of the statement 1. So first option is correct. Next is the load transfer mechanism in MMC is explained by the shear lag theory. Next question, means shear lag theory gives the shear stress acting along the matrix interface, means this is sigma, means the normal stress, and the shear stress is along the L/2 part. So this explains the load transfer mechanism in metal matrix composites, and the L/D ratio also determines the strengthening effect comes from the fiber reinforcement. So a definite amount of definite length of the fiber is required for providing the good load transfer ability from the matrix to particle, matrix to fiber. Next question is the shear lag theory shows that load is transferred to the fiber through the interface. So load is equally distributed throughout the MMCs. No. Shear stress is less in fiber than reinforcement. No load is transferred to the fiber through the interface. So the third option is correct. In the fifth question, the discontinuous fibers reinforced composites will always have lower strength than continuous fiber reinforced composite. Statement 2 says the strength of fiber reinforced composite depends on the length of fiber. Yes, so both statements 1 and 2 are true. Means it depends on the length of fiber. So the D option is correct. In the sixth question, it is asked that the Oro-1 strengthening mechanism deals with the bending of dislocations around impenetrable solid particles when they are dispersed in a matrix phase. And the statement 2 says the formation of the Oro-1 loops makes the dislocation motion difficult. This results in large work hardening. Yeah, it is results in large work hardening also. Or leads to Oro-1 strengthening. But the Oro-1 strengthening also creates dislocations. And will act as dislocation generated source. So, good evening, all. Today we discuss about the week 10 lectures. So, in the week 10 lectures, we will further study the different mechanism of the particle matrix interface and the engulfment or pushing of the in last weeks we studied the in what mechanism means solidification condition leads to the pushing of the particles or either um, engulfing of the particles by the matrix. So let's start further. So how the molten matrix how the solidification front and the particle interface behave during the solidification process. So if we consider this particle and the solidification front along beside this, so here are many forces acting on the particle due to the solidification front and the molten matrix. So if we see that this is liquid and this is solid, and the solid front is moving with a velocity v, and the forces acting on the particle will be, so this is x direction and this is z direction. So z is the heat flow direction. So for this the some forces acts on the particle, which is I am mentioning. First is Fi. So the radius of this particle is r, and the radius with the solidification front will be ri. Then Fg, gravitational force, and the Fd, which is drag force, and the distance between the solidification front and particle assumed as d. So at the solid liquid interface, thermal gradient exists because of the temperature difference at this interface. And for that the heat flux will be this g. So for a spherical radius of spherical particle, of radius r, v is the relative velocity of particles, v is the relative velocity of particles, not the solidification front. Less means relative of particles. G is the thermal gradient and D is the separation. At x equals to 0. So if we write the interface radius with the particle Ri. The formula will be 2a minus b divided 3a and the r plus d. So here a will be the 1 minus alpha, 2 plus alpha, and b will be 1 plus d by r का whole cube. If d is very less than r, then b will be 1. So therefore the Ri will be 2a minus 1 by 3a r. So if we dissociate this equation, this term, 2 minus 2 by 3 minus 1 by 3a and 1 by 3. If we extract it, then 2 minus a is the 2 plus alpha by 1 minus alpha. If we further equate this will be alpha by alpha minus 1. So Ri will be r alpha by alpha minus 1. So this equation will be 2 and this equation will be 3. So alpha is the ratio between the particle thermal conductivity and the matrix thermal conductivity. So for alpha less than 1 means the particle thermal conductivity is less as compared to the matrix thermal conductivity. So from this equation 3, if we see if the alpha is less than 1, then Ri will be less than 0. Means interface will develop a bump. Means this type interface will create a bump, so this will push the particle. And if the alpha is equals to 1, then Ri will be infinitive, because the alpha minus 1 is in the denominator term, and for Ri tends to infinity, there will be planar interface. For alpha greater than 1 means particle thermal conductivity is higher than the matrix thermal conductivity, means Ri will be greater than 0. So for that a draw will form, means this type of shape will form. So this will lead to engulfing of particle. So the forces acting on the particle are on the particle will be, first is the gravitational force, Fg. Second is drag force, Fd. And third is the force due to interfacial energy. This is Fi. Means why the interfacial energy comes into picture. The van der Waals forces between the solidification front and the particle. So this will be because of the van der Waals forces with interface. So if we see the gravitational force, Fg will be mg, that will be 4 by 3 pi r q delta rho g, and the delta rho is the relative density between matrix and particle. Rho m is the matrix density and rho p is the particle density. So if delta rho is greater than 0, means matrix density is higher than particle, then Fg will be upward. Means up, if Fg is upward, then pushing effect will come, and if delta rho is less than 0, then Fg will be downward, means engulfing. And for the drag force, we will go to the Stokes law. So the drag force will be 6 pi eta Vr. N is the viscosity of melt. And for a planar interface, the drag force will be 6 pi eta V. If we put here the atom, r square by d, for d very less than r. This will be 6. And for non-planar interface, means straw or bump, means there will be, for non-planar interface, there will be a radius Ri, which we derived just earlier. The Fd force will be 6 pi neta r, so this is b r square d ri by ri minus r का whole square, and the ri by ri minus r is equals to alpha. Alpha and then fd will be 6 pi neta v r square d into alpha square. So the drag, what are the sources of drag force? So this will arise due to flow at the interface behind the particle. So for the concave radius means there will be drop, alpha is greater than 1 and ri is greater than 0. So drag force will be higher, and for convex means the bump created, alpha is less than 1 and ri is less than 0, so drag force will be less. And next is the interfacial force Fi. So Fi is written as the 2 pi r, means this is the perimeter of the solidification front, perimeter of the particle, and the delta sigma. Delta sigma is the difference between interfacial energies. So delta sigma is written as sigma naught a naught plus d whole power n. Here n varies from 2 to 7. E naught is the sum of radius of surface atoms of particles and the solid. So again, for planar interface, the interfacial force will be 2 pi r delta sigma naught a naught plus d or n. Here one thing is that the sigma naught is the sigma sp minus sigma lp plus sigma ls is, means this is the surface energy, interfacial energy between surface solid and particle, sigma ip means interface liquid and particle, and sigma ls is the liquid and solid. So next is for non-planar interface. The fi is 2 pi r delta sigma naught a naught plus d over n and ri by ri minus r means alpha. This is alpha term. So fi will be 2 pi r delta sigma naught a naught plus d power n alpha. So when a naught plus d is very less than r particle radius and the alpha is greater than 1, then concave interface will form and fi is increased. And alpha is less than 1. And convex interface means for this fi is decreased. And the delta sigma naught value, if it is greater than 0, then fi is conducive for pushing and for delta sigma naught less than 0, fi is conducive for engulfing. So a critical velocity of particle also required for the interaction between solid particle and the solidification front is that it is so a critical velocity is defined vc. So vc is the function of particle size and temperature gradient. So for a critical separation, DC, critical separation between the particle and solidification front, DC can be written as the A naught n minus 1. So critical velocity of the particle will be A naught delta sigma naught divided by 12 beta alpha r. So for n equals to 2 in this equation, or in this dc will be a naught. So for the above the critical velocity above bc, the front solidification front grows and engulf particle, and below the vc there will be pushing of particle. So a critical velocity is required for the engulfing of particles in the matrix. So up to this point we studied the effect of weighting of particles and the solidification condition on the particle matrix interface, and the for the uniform distribution of particles in the matrix phase. So now we will study the rule of mixture, means what are the concept behind the addition of fibers in a certain amount in the matrix. So for that we studied the rule of mixture. Means rule of mixture is the a weighted average of properties. Properties of matrix and reinforcement. So we see the three types of reinforcement in a matrix. First can be the continuous reinforced composites, means the fibers are continuous throughout the matrix. So this is called the continuous reinforcement. Second will be the particle reinforcement, that is means particles are embedded in the matrix, and the size of the particles can also vary. This is the discontinuous reinforced particles, and these are the fibers. So this is called discontinuous. Reinforcement. And third will be the if the fibers are cut and then mixed, so that will be called as the whiskers. and align in one defined direction. So these are the short fiber reinforced composite. So three types of arrangement of reinforcement can be seen. First is the continuous fiber, second particle reinforcement, and third is the short fiber reinforced composite. This is also the discontinuous reinforcement. So the if the matrix has a modulus EM and the fiber modulus is written as the EF, then the composite the modulus of the composite can be written as the EC equals to EM VM plus EF VF. So this is called the weighted average of a properties between matrix and particles, matrix and reinforcement. So here VM is the volume fraction of matrix, and this is for fiber volume fraction. And as the volume fraction addition of means sum of volume fraction of matrix and fiber will be 1, means VM can be written as 1 minus VF, then EC will be EM 1 minus VF, EF and VF. Means the whole reaction can be written as the in terms of particle volume fraction. So this equation is also considered in the isostrain condition. Isostrain is what? Means the matrix and reinforcement is deforming at the same pace, means with the same loading rate, and the deformation rate is also same for the matrix and the reinforcement. So if we see this is the continuous fiber, and tensile load is applied. So the strain of the composite, strain of the fiber, and strain of the matrix is same. This is called the isostrain condition. It's all phases are deforming with the same amount. And the cross-sectional area. So if we write the load acting on the composite PC, composite interface PC will be sigma FAF plus sigma m am means the cross sectional area of fiber multiplied with the stress acting on the fiber, and plus stress acting on the matrix multiplied by cross sectional area of the matrix. And the cross sectional area of the composite will be the addition of cross sectional of fiber and cross section of matrix. So further, the sigma can be written as the log divided by the cross section of the composite, and sigma c will be written as the sigma f af by ac plus sigma f am sigma m am by ac. So if length of composite is L and we write the term am by ac and multiplied by L, so this will be volume Vm by Vc means volume of matrix, volume of composite. Then this will be the volume fraction of the matrix, and similarly for fiber this will be Vf by Vc and volume fraction of fiber. And the volume fractions for both will also written as addition equals to 1. So sigma c will be sigma f ff plus sigma m 1 minus f. So the isostrain condition means em equals to ef equals to ec is only valid for the elastic region. Means this is the elastic behavior. So the sigma m is written as the modulus of the matrix and the strain in the matrix. Similarly for sigma f, ef into e small ef. So if pc is written as ec to ac equals to ef to af plus em am and em. So as the strain in composite, fiber and matrix are same, this term will cancel out and we will get the ECAC equals to EFAF plus EMAM. That can be further written as the EC equals to EFFF plus EMFM. So this is how we can derive the weighted average of the elastic modulus of composite from the rule of mixture. So for the continuous fiber only, if the stress strain curve is drawn, sigma epsilon. So first we'll draw the stress strain curve for matrix, slope is very low with high ductility, and for the reinforcement there will be very low plastic deformation, and it will fail early. This is the fiber. So the composite stress strain curve for composite will follow this line, means the weighted average of both. Further, the stress strain curve of the composite is it also divided into three regions: stage 1, stage 2, and stage 3. So stage 1 is the elastic deformation of both fiber and matrix. Stage 2 will be where matrix will deform plastically, and fiber is still elastic. This is called the quasi-static strain rate, quasi-static condition. So this can be written as the EC equals to EF FF plus D sigma by D epsilon power M FM. So this is the strain hardening in matrix and plastic term. So if the strain hardening is very less than the elastic modulus of matrix, then this can be written as the EF and FF, means the modulus is only considered for the fiber. And matrix will develop. So in this condition, a compressive stress, because fiber come back at the initial length after unloading. So matrix will develop compressive stress at the stage 2nd. For the stage 3rd, both fiber and matrix deform plastically. So for this condition, the stress can be of the composite can be written as the Cu sigma Fu, the volume fraction, plus sigma m dash 1 minus ff. So fibers can but the fibers can fracture at the stage third because they don't have any plastic deformation, considerable plastic deformation. And here sigma m prime is the flow stress of matrix at strain.